Hello everybody. Hope things are going okay with you all. I'm checking in to make sure everything looks good here on online on our D2L site. I'm checking in on, let's see, scheduling and stuff. Yep, all good there. Okay, so I've had a chance. I just got done grading and entering the homework for your that you turned in last week on Sunday. So that should all be posted. I also wanted to mention that, by the way, should say hi in this chat for anyone that is showing up here, just so I know who's present and stuff. Thanks for coming along. I do want to mention, like I said, I did get the homework graded. Also, if you are looking for feedback from that, even if you got the answers right, I might have left a little bit of feedback there for you to look at. So I strongly suggest that you have a look at how that played out. I can give answers or give little hints if you didn't have the answer quite right, even though you got all the points. Hey, how's it going, Samantha? Even though you got all the points, there might have been something slightly off on it. Remember, I said I was going to be a little bit generous on these homework. Hey, Zach. On these homework problems and stuff like that, so that folks are still getting the points. If they basically got it, looks like they got it, but if there was something slightly off, I didn't take off points, but it did leave feedback for you to look at. So you can check that now. I've added an extra view, so even though the quiz is already done, of course, you can go in and you can click on, well, let's see, maybe I can show how this looks. Let me bring it over here. This is how it'll look for me, but let's see, I'll just bring this over here so you can sort of see what I'm talking about here. So I'm going to view this as a student so you can have a chance to look at this. So this is sort of what your view would look like. If you go under assessment and you go to quizzes, okay, I don't have any submissions done or anything like that, but what you could do is you could go down to, say, I don't know, homework, whichever one's graded and got points in. You could go to the homework, and you go under submissions, and when you go under submissions there, if you've actually attempted it, there'll be a list right here, and a little arrow that allows you to click down, open it up, and then you can open up the submission, and then when you look at all the questions, there's a little spot, like a little, where you can expand and see the feedback for each question. Now, if you got it right, and it was, dead right, and there was no problem with it, then I didn't leave you any feedback. If there was a mistake, but you still got it right, you still got full credit. You can still click on the feedback and it can say, oh, you did, there was a little arithmetic mistake here, or maybe, oh, here's a slight error in the way that you were thinking about this particular one, and it'll show, I'll tell you what that is. So even if you got them all right, you might want to check the feedback that if something wasn't quite right, even though you got full credit, you can still check and see what, where your ideas might have been a little bit off or something like that. So hopefully that's useful information to folks, and that should be available on other homeworks that I've graded, like the week before, from the week before and stuff like that too. So there's all those possibilities. So let's see. What about questions for this week? How are things going with the idea of DC circuits? Because that's the main idea about what we've been working on here over the last for this last week, and this will be the last chapter that we will be dealing with before the next exam. So just as a prelude, I think I made it clear next week you should plan on having an exam, and I'm thinking, for exam 4, same format as we had before, but we'll have a short review on Monday. And then probably I will have a review live stream on Tuesday, and then it'll be open the second half of the week. So that's sort of what I'm planning so far, but I think that should work out with what we've been talking about lately. So I think what I want to do now is, and like we've done before, if you have questions, feel free 100%, just pop, even if it's not related to what I'm talking about right then, just pop your questions into the chat immediately here, and I will get to them as soon as I finish my thought, and then we'll have a look at what your questions is to make sure that they get answered. So that's what my plan is for next week, and then what we're doing here today. So, all right. So, Sam asks, is it possible you could tell us how many of the devices were ohmic or non-ohmic? Let's see. For which, are you talking about for lab now, Sam? I'm not sure what the basically. Let me just talk about what ohmic is versus non-ohmic. Okay. So, if you have a graph, let me see. We got the wrong. There we go. This will be a little bit easier to see for y'all. So let's say you plot. I'm not sure which way I asked you to plot, but I think usually what I do is I say plot current as a function of voltage. Because usually what you want, okay, for the lab. All right, so you should plot the current as a function of the voltage that is applied. Usually I do it like that because usually what you do is you have like the independent variable on the x-axis and the dependent variable on the y-axis, and you notice that when you turned up the voltage for the device, for the little voltage source that I built there, then there was a resulting current. So an ohmic device will be one where you have a line. Okay, that is, and what that means is, notice that if you say that, if this is true, this is Ohm's law, V equals IR, which implies, if I resolve this for, the Y equals MX plus B sort of thing, I is equal to 1 over R times V. So, let's put this in parentheses. So 1 over R would be the slope of this line. If the resistance, in other words, the slope of this curve that we get here, if the resistance changes with different voltage, then you would have a non-ohmic device. Okay? So this is a graph of an ohmic device. If instead I had, I'll draw it in a different color here, if I had a device that did something like this, where notice how the slope changes with depending on what voltage I have, that means my resistance is changing. That's a non-ohmic device. And it's one where it's not really that Ohm's law doesn't hold. It's just that R isn't a constant. So that's what a non-ohmic device means. So I guess I don't want to necessarily answer exactly how many of the devices were ohmic or non-ohmic, but this is what I'll say. Hopefully you noticed that the resistance of a device that's called a resistor is constant. It basically stays constant. So that should be a big hint, because we only had 3 devices. We had 3 resistors. Yeah, so hopefully that's what you saw. If you didn't, then there might be something wrong in the circuit or something like that. Hopefully not, though, because in my tests of my little demonstration circuit, it seemed to work as I expected it. Okay. All right, glad that was helpful. Were there other questions that folks had about things? So I'm going to clear this out so we have a little space. Not usual. Okay. So one thing I wanted to go over with, because it's hard to make this come through in the lecture notes because it's kind of hands-on and visual, but not in a static way. It doesn't work so well. Is the idea of the 2 ideas of how to analyze circuits using Kirchoff's rules. Now, I'll mention this too because I've had it happen in the past where there are folks that have somehow taken the courses in physics and engineering a little bit out of order. And one of the things you could do then, if you were going to do that, is you might take your circuits class before you took this class. This class is supposed to be the prerequisite for circuits. But sometimes folks got them out of order and they were allowed in to take circuits first just because that fit their education plan better. It's not ideal, but it's possible. But it means that you don't necessarily understand the basics of how things work. There's lots of techniques that if you're going into circuits next semester that you're going to learn that are based on what we've talked about here. There's mesh analysis. There's all sorts of different techniques that you can use to solve circuit problems like we've been discussing this week. I know that there may have been folks that know that stuff. There could be. Maybe you went out and you learned some circuit analysis or something like that. But what I'm asking you to do is, even if you know those things, I want you to use Kirchoff's rules for this. And there's a reason for that. Normally, remember I say, I don't care how you solve a problem, just get it right, and I'm cool with it as long as the method is sound. The problem is that all of those other methods that you might learn in circuits are based on Kirchoff's rules. So I want you to, even if you said, oh, this is so complicated, I don't want to use Kirchoff's rules, I've learned this other technique. If you don't understand how Kirchoff's rules work very well, then you don't really understand that technique. You can't apply those techniques very well. So that's why I'm going to ask you to use Kirchoff's rules here. So I'm going to demand that you use Kirchoff's rules. Don't use mesh or nodal analysis or stuff like that you may have seen if you're not new to circuit analysis. If you are new to circuit analysis, then you're getting the basics and you don't know what I'm talking about and you don't have to worry about it. But let's look at really a simple circuit which could be analyzed a couple of different ways, a very large number of ways in fact, where I've got a battery and then I hook up the battery. And remember, this is the positive terminal of the battery, this is the negative terminal of the battery. Let's say that I have a device here. This is the symbol for a resistor. Okay, so it's a squiggly line. I'm going to call that R1. And then there's a junction right here. And it splits, and some of what happens, in this case will be the current, will go through R2, and then there's a third resistor over here. And this is a pretty simple circuit. Goes up here and connects to the battery like that, and this will be R3. Okay, so let me tell you then a little bit about the analysis types that I would definitely want to do. What would I do to analyze the circuit? There's two different ways that you could solve this circuit. This circuit, because there's one battery and there's, resistors are in series and parallel with one another. R2 and R3 are in parallel. R1 is in series with that combination. Hopefully you can see that geometry. This circuit can be analyzed by just finding the equivalent resistance and then being done with it. You can find the current that goes through each resistor. That's kind of usually the problem. By finding the equivalent resistance of this whole circuit, all these three resistors together, excuse me, and then seeing how the current splits and all that. So that's one way to do it. The reason that works here is because there's a single battery that is not in sort of a, in a branch of the circuit. You don't have multiple batteries and multiple branches of the circuit. If you have batteries that exist in like here in this branch and in this one here, then you can't simply reduce it to an equivalent resistance style problem because there's more than one source, and there's not just one. There's more than one source of voltage, more than one source of current. In that case, you need to apply Kirchoff's rules. Okay, so this one can be done either way, but let's analyze it versus using Kirchoff's rules first, because Kirchoff's rules are like the nuclear bomb of this. It's the brute force method that always works. It may not necessarily be simple mathematically, but it's a way that always works. And by mathematically, I mean it generates a set of multiple equations, but it's that becomes an algebraic solution. The algebraic solution may be tedious, but it's guaranteed to be right if you can do algebra. Okay. All right, so here's the deal. The first thing you do to solve a Kirchoff's rule problem is you're going to label all the currents. And sometimes, because of where voltages are in your circuit and stuff like that, you may not know which way the current's going to flow. It's actually not a problem. If you don't know, guess. Just guess. So it'll come out on the wash in the end. So let's say that let me do this a little bit differently. What I'm going to say is that there's a current that flows in this branch here. And notice that between here and here and the wire that I'm talking about, between this spot and this spot over here, there's nowhere for the current to split out. So the current needs to be the same in all of this region here, and I'm going to label it up here at the top as traveling this way, and I'm going to label it I1. And the reason I label it I1 is because it's going through resistor 1. Now, if the current is flowing from left to right at the top, that means in this branch it would also be flowing from right to left in the bottom part of the branch. It's also I1 down here. Okay? Because this branch right here, there's nowhere between here and here where it could split in the process. Okay, so that's one of the currents. The thing is, there is a junction right here. So as current flows into this region here, some of it goes here and some of it goes down here. So this is what I'm going to do. I'm going to say this current here in this top branch here, I'm going to label, not surprisingly, I3, because this is the current that's going through R3, and this current here, which I'm also going to have going down here, I'm going to call I2 because it's the current that actually flows through resistor 2, and it's in this branch. Now notice that in this branch right here, that actually is I3's branch because of between this spot up here and traveling through the resistor and going down here, there's nowhere for it to split off, so the current needs to be the same in all those branches. Okay, now how do I apply Kirchoff's rules to this situation? The way that I do it is there are two rules. As if you haven't gotten to it yet this week, super important that you get to it soon, because Kirchoff's rules are like, it's probably one of the reasons why we've been doing electricity at all. It's so that you can understand how circuits work. So there are two rules, two basic rules. One of them we call the loop rule, and the other one we call the junction rule. The loop rule states, so I'll just state it rather than writing it because it's a pain in the neck to write on this, a long rule. But the Kirchoff's loop rule says that the sum of the rises plus the sum of the drops in any closed loop has to be 0. This is a consequence of the conservation of energy. So what you do is then you choose a path in your circuit, and there'll be voltage rises and voltage drops in that path. And when you sum up all the rises and all the drops, they have to sum up to 0. So any time you go up some number of volts, somewhere else in the circuit you have to go down that same number of volts so that the total is 0. And the reason is, if I start, say, from here, and I go all the way around, say, this loop that I've chosen, this arbitrary loop, pick whatever loop I want, when I get to here, the change in voltage better be 0. The voltage that's at this spot right here better be the same whether I start there or I finish there. I can't have any overall change in voltage. So that's one of the rules. But notice, it doesn't specify what type of loop you want to do. It's any closed loop works. So, for instance, I could choose this loop. Some of the voltage rises in that loop plus some of the voltage drops has to equal 0. But if I go around and say, I'm not going to take a right-hand turn at this spot, I'm going to keep going straight and go through this one, that has the same circumstances. It's got the sum of the rises in that one, the sum of the has to equal the sum of the drops. I can go here. Some of the rises, some of the drops. I can go in any direction I like too. I could go around this way, or I could go around this way. It doesn't matter. I just have to pick whatever one is particularly convenient for me. Okay, now here are some of the rules about how to count whether voltage across a device is a rise or a drop. If I go across a battery, moving from the negative terminal through the battery to the positive terminal, that's a rise in voltage. However, if I was going the other way, so let's say I was going around in this particular direction, and I go from here down here, notice I'm going from the positive terminal of the battery to the negative terminal of the battery in my process of traveling around in my loop. That's a drop in voltage, equal to whatever the terminal voltage of the battery is. So if this were a 9-volt battery, if I went this way across the battery, I would gain 9 volts in traveling that way. But if I went this way through the loop, I would drop 9 volts, and I would have a change in voltage of negative 9 volts going from there to there. Okay, so that's one thing to keep in mind. So when you cross a battery, if the way that you travel in your loop goes from negative to positive, that's a rise. If it goes from positive to negative, that's a drop. The other thing is, when you travel across a resistor and you travel in the direction of the current, there's a drop in voltage. If you travel the opposite way when you're describing your loop, going from, say, here to here, notice that that's going opposite the direction the current is flowing through the resistor. That actually corresponds to a rise in voltage. And that's that. And that's it. Now notice what I said. You have complete flexibility in the direction you want to travel in going around in your loop. I could go clockwise or I could go counterclockwise. It does not matter. You just have to keep track of the signs correctly. Either way, it'll be consistent. You just need to be consistent within it. So that's an important factor about how to apply the loop rule. Okay, so that's the loop rule. Like I said, you could choose any loop. I could go from here, I can go down here, I could come around here, come back like this, and then finish going back through the battery the other way. That's a crazy loop, not particularly useful, but you can use any loop you want. You can go whatever direction you like, whatever notional idea you have about, I want to go clockwise. Okay, no problem. Then just make sure and follow the rules. I could go this way, no problem as well. So let's actually perform a loop rule. Let's go around and let's see the alternative if I went the other way. So let's say that I start here, start at this spot, and I'm going to go around this loop in this direction. So as I go from here to here, I gain whatever voltage the battery has across this terminal. So I put plus V. So I go from there to there. Okay, then I cross from here to here. And there's a voltage drop across resistor number 1 because I am traveling in my loop path across the resistor in the direction that the current is flowing through the resistor. So minus, now whatever voltage there is across the resistor, using Ohm's law, I know that the voltage across a resistor is equal to the current that flows through it times the resistance of that resistor. So there we go, it's I1R1. So there's the voltage drop across that resistor. Now, I'm going to continue my loop and go through this resistor. Again, notice I'm going in the direction that the current in that particular branch is traveling, at least the way that I labeled it. So there's a voltage drop across resistor number 2, which is equal to the current that flows through it times whatever its resistance is. Okay? And then I get here, and I say, well, I'm going to continue traveling across, till I get back to where I started. Notice that there are no devices in this little sub-branch of that circuit, so there's no voltage drops. This is just a wire with no resistance, no voltage drops, so I'm to the end. I'm back to where I started. So the sum of the voltage rises and the sum of the voltage drops together here should add up to 0. That is the loop rule for this loop. Okay, so hopefully that's clear. What I'm going to do now is I'm going to say, just so you have a sense about what this is let's say I want to go the other way. I'm going to go in the counterclockwise fashion now. I'm going to start here. I'm going to finish there going through these resistors and then through the battery. All right, so let's see what that does. Hopefully you can kind of see what happens here, but let's just do it. Okay, so I start from here. No devices cross as I go across here. So no voltage rises or drops. And as I go from here to here, I'm going clockwise or counterclockwise, remember. Notice here I'm going up through the resistor, and I'm going opposite the direction the current is flowing. So like I said before, that would indicate a rise in the voltage. In this case, it would be I2 times R2, again using Ohm's law. The voltage has increased in going from here to here. Okay, and I'm going to continue the same loop I did before, just going the other way. Now I'm crossing resistor number 1 in my loop. Okay, well, again, I'm crossing the resistor in a direction opposite the way the current is flowing, so there's a rise in voltage, I1 times R1. Okay, so now I'm here. Okay, so that's the resistance, or the voltage rise across resistor 1. And then I get here, and I'm going to cross the battery. Notice I'm going from the positive terminal of the battery to the negative terminal of the battery. So what happens when I cross that is I lose whatever the voltage is on the battery. Okay? I've decreased the voltage in going from there to there. And then I'm back to where I started, so that should be equal to 0. Now hopefully you notice the relationship between these two equations. They're the same equation, except with a minus sign in front. But since negative 0 and positive 0 are the same thing. It's the same equation. So going around one way and going around the other way give you the same equation. It's just that the sign of every little term in it gets switched. So hopefully that's relatively clear. So it doesn't matter which way I go. Okay. So there are a bunch of other different little loops that I have here. So another loop that I could have chosen instead of this loop here, I could have like the big loop. Okay, that goes all the way around, skips R2, but goes through R3 instead of R2. So what I'm going to get there is, hopefully you can sort of see this, plus V, minus, again I'm going through resistor 1, in the direction the current is flowing, so minus I1R1, minus, but instead of going through resistor 2, now I'm going through resistor 3, again in the direction of the current, that I've drawn at least, I3R3, and then I get down here and I continue through to the end point. There's my loop. Okay, so that's, a second loop. And it gives us new information about how the circuit works. Now, you could say, well, I've got 3 currents here, but I've only got 2 equations. So you're right, this one we couldn't solve using just these 2 equations because I have I1 to solve for, I2 to solve for, and I3 to solve for, given that I know what the resistors are and the voltages. So what's the, well, I need a third loop, obviously. I need a third algebraic equation so I can solve for my 3 equations and 3 unknowns. Well, we could do this little loop here and skip the battery. So I don't know, let's start here, because why not? I can start anywhere I want. Let's go clockwise, I guess. No reason why I chose clockwise, just because it doesn't matter which one I check, because if I go the other way, I'll just get the same equation with minus signs in front of all of the terms, so I get the same equation. So let's see what we get here. If I go clockwise around this, I'm going in the direction of the current I3 as it goes through resistor 3. Okay, and then when I get here, and so nothing here, and then I'm going to go up here to finish the loop. Notice here I'm going opposite. So it's going to be up. Okay. So there's that. Now here's the problem with this. This actually doesn't give us any new information. Because if you look at this, this doesn't give us any new information compared to what I have here. Because notice what this says is I2 times R2 is equal to I3 times R3. That's what the third equation means. But if I do that, if I plug in, I3 is the same as I2 times R2, and I plug it in here, notice I get the same equation as this one. If I say I3 times R3 is equal to I2 times R2, yep, that's true, okay. That's basically the idea that these two are in parallel, therefore the voltage difference across the two is the same. Okay, that's what this part of that loop really means. But if I plug that in here, I get that this equation, the top equation here and the bottom equation here become the same thing. So I know I'm actually not learning any new information from this third equation. In other words, this equation here is redundant. The loop rule actually only is going to give you, doesn't give you completely unique information. No matter if you use, I could make the loop that goes around 3 times. That's not going to give me any more information than this first equation, is it? So it turns out that because of the geometry of all circuits and the way they operate, the loop rule by itself is never enough to solve for all the currents in the problem. You're always going to come up one equation short. No matter how many loop rules you do, you're always going to come up one equation short of being able to solve it uniquely. The way to talk about this, if y'all are in like linear algebra and multivariable calculus, and your calculus that has linear algebra in it, because of the nature of the loop rule and how circuits work, these 3 equations are not linearly independent. 2 of them are linearly independent, but the third equation is a linear combination of the first 2. That's tells you that if you're in that multivariable calc class, or in that calc class that has linear algebra and differential equations in it, it turns out it's useful. So this equation right here, while it is true, is not particularly useful. So let's talk then about what is an equation that's useful. There's the junction rule. So Kirchoff's rules come in two varieties. There's the loop rule, which we've just been talking about, and then there's the junction rule, which I've already labeled where my junction is here. That was fortuitous. Okay, so the junction rule says is not a condition on the voltages like Kirchoff's loop rule is. It's a condition on the currents. It says that if you pick any junction, choose any junction in your circuit, the amount of current that flows into that junction must be equal to the current that flows out of the junction. That is purely a consequence of the conservation of charge. So if 3 coulombs per second happen to be flowing towards this spot right here in my circuit, right there, then a total of 3 coulombs per second have to be leaving. Otherwise, charge is building up there, or something like that. Or you're losing charge. There's a leak if there's less coming out than went in. So our junction rule here is, okay, I1, that's the total current that's flowing towards the junction right there that I've labeled. And that has to be equal to however much current is flowing out of it. Well, I2 is flowing out of it. And I3 is also flowing out of it. This gives us a third independent equation for the currents. So this means if I have 3 amperes, 3 coulombs per second traveling towards that junction, if this is 1, then that has to be 2 amps if this is 1 amp. That's all it means. Okay. So hopefully this has been helpful. If you could just give me a thumbs up, or that you're listening, or that it's useful. But this is sort of the general way that you set up an equation with loops and junctions and that sort of stuff. And this will work in every circumstance. Kirchoff's rules always work, even for the simple circuit where there's only one resistor even. So that's kind of how to solve it. Now, here is a thing that I'm not going to show it to you necessarily, but I'm going to tell you that this is true. At the beginning, I said I labeled my currents and I indicated the direction that they were flowing. That's important, but I said you might not know which way the current is actually going to go in any particular branch. And this might be true if, like, what if I have a battery in here that's got a really, it's like this is a 9-volt battery and there's a 12-volt battery here, something like that. What do you think, is the current going to flow to the right or the left? Well, it kind of depends on how it splits. Yeah, I'll go over units in just a second, exactly. Good point, Sammy. Okay, so you might not be sure exactly how the current splits out. And you might not know whether the current in this branch actually goes to the right or the left compared to that junction. So you're going to have to guess. The thing is, when you do the algebra and you solve for all your currents, if you get a negative current, it doesn't mean you did something wrong. It just means your guess was incorrect about the direction of the current that came out negative. So all that means is, so for instance, if I make a guess that I3 is to the right, and then I go through all my algebra and I find, oh, I3 is a negative number. All that means is the actual current that flows towards the junction rather than away from it in this case. That's it. No problem. Kind of like back in the day when we were doing the equilibrium problems and torques and all that sort of stuff, and you had unknown forces, and we had to guess which way the force pointed, was up or down or right or left or whatever. And we found out, sometimes you find out at the end that the force that you calculated comes out to be negative. But then all that really meant is that you guessed wrong about what the direction of the force was. The same thing is true here. So just note that what I would do if you were doing a solution like that and you get a negative current, just say the current in this branch is equal to whatever number of amps. Take the absolute value. And then from there, just say, and the direction that I chose was incorrect. It actually goes, away from the junction or whatever. You just decide, to the right or to the left or up or whatever. So just indicate that you recognize that you got the direction wrong. So Samuel was asking about could I go over units? I sure can, no problem. And it's somewhat the units of resistance. So the units of resistance are in ohms. Okay, so I'll just say I'll put a dash line in, and we use this symbol for ohms. I think I went over it last time why we use that symbol for ohms, because ohm is a person. When we take a person and we say we're going to honor them by giving them a unit that's associated with some physical quantity that they were instrumental in discovering or something like that, we usually we're going to call it ohms. The problem with ohms as a unit is because the abbreviation would be capital O, which looks a hell of a lot like a zero. So we reach into our bag of Greek tricks and say, well, we're going to use the Greek letter for O, which is omega. Okay. So from Ohm's law, I just use Ohm's law so often with this. It tells you what the ohm actually means. The volt, V, the voltage is in volts, which is a joule per coulomb. So if this is in volts and I is in current, then the unit of resistance is the same as the units of voltage divided by the units of current. So the voltage is in volts. The current is in amps. So a resistor has a resistance in ohms, which is the same as a volt per ampere. The ampere is a coulomb per second. It's the amount of charge per unit time. A volt is the same as a joule per coulomb. So you could use, a volt per amp being a resistance. You could reduce this to basic units if you want. You could say it's joule per coulomb, divided by coulomb per second. So it's like a joule times a second. I don't know, something like that. I don't remember. Something like joule per coulomb, and then divided by a coulomb per second. So it's a joule second or something like that. Is kind of the basic, and then you can find joule as a Newton meter, and a Newton is a kilogram times a meter per, times meter per second squared, something like that. So you could put it in basic units if you want, but that's sort of it. Is that helpful, Sammy? Is that what you wanted to know about? So an I times R always ends up being a volt because resistance is a volt per amp and the current is in amps. So this is a voltage. This comes out to be a voltage. Obviously, that's a voltage. So hopefully that was helpful. Then the other thing to note is that the unit of power is the watt, which is a joule per second, which that's something we've talked about in the past, but it's no different than it was in the past. Okay, thanks. I'm glad that was useful. Okay, so were there any questions on how to do this sort of analysis? So I'll mark time a little bit by talking really briefly about this, but ask your questions now about how to perform analysis like this and current. And you also don't forget you can ask questions on stuff previous to this too, like how do we do these, combining resistors and stuff like that. Very similar to capacitors, but with a little bit of a twist that the series formula looks like the parallel formula and vice versa. But the thing I do want to mention here as well with this is about how I grade problems like this. What I want you to do, what I really want you to be able to do, the skill that I want you to have, is to be able to write down these loop rule and the junction rule equations. At the end of the day, because with complicated circuits, these loop rules and junction rules can look extremely complicated. There's all sorts of challenges in solving them algebraically. So I'm going to say 80% of the points in any problem that involves an analysis using Kirchoff's rules is going to be, did you get the loop rule and the junction rule right? Did you get a set of equations that you could in principle solve? That's 80% of the points. So 8 out of 10 points that would be available on that. If you get that right, you got 8 out of 10. The last 2 points are, can you actually do the algebra and solve the problem? in a lot of ways, it's like what we did with finding electric fields and integrals. 80% of the problem, of the points in the problem, are contained in, can you set up the integral? And the last 2 out of 10 points would be, can you actually solve the integral? And again, for exams and stuff like that, I would be creating the problem in such a way that the algebra will be relatively simple if you make a couple of astute observations at least. So I don't want to make the algebra hard. Now, that said, in homework problems, all bets are off. I could give you any sort of circuit analysis sort of things that I want because you've got more than 10 minutes to solve it. You've got days to work through the algebra if you need to. Not that I really want you to like suffer through hours and hours of algebra or something like that, but I do want you to at least recognize what the what needs doing and what techniques you can use. But that said, don't hurt yourself with all of that algebra if you've got a device like this that you know how to enter sets of equations and they can solve them for you, then use this tool. Whatever it takes. Put it in Mathematica or Maple or your calculator or some other symbolic manipulation piece of software, and feel free to use it. I'm not requiring you necessarily to go through and do, Gaussian elimination to get the set of equations to reduce row echelon form. Again, if you're in if you're in linear algebra, you know what I'm talking about. If you're not in linear algebra, and I think it's Calc 4. Yeah, I think it's Calc 4. But if you're not in that yet, you'll eventually know what I'm talking about. But anyway, so I've been gabbing on here a little bit about stuff, but hopefully it's been useful. What other things do you all want to know about? Again, don't hesitate. If you've got something to ask in the chat, I'll definitely get to it. If you want to see an example problem done, or you've got question on homeworks that are coming up, like I said, I did get a chance to grade all of the homework from last week. This week, there aren't too many that are in yet, so I haven't graded those yet. But some folks have handed in their homework that is going to be due on Sunday. They've handed it in already, but I haven't looked too much at it yet. You want to see me do something concrete with this? Go through an example problem that was in class. What's the? Oh, I should mention one other thing here. So back to the analysis of this relatively simple circuit. There's another junction that you could be looking at here. The other junction you might consider is this one right here. Down here. That's because this is where, the currents rejoin and then flow out. Well, in this case, what current is flowing towards this little node right here, this little junction? Well, I2 is flowing towards it. And I3, after you get around here, is flowing towards that junction as well. So I2 plus I3 is the total current flowing towards the junction. And that's it. And I look at I1, and I see I1's flowing away from it. So it's the only one that's actually flowing away. So you'll notice that this equation right here and that equation here are essentially the same. It's redundant again. In the same sort of way that this third equation down here was redundant for as far as loop rules was concerned, there's never just one junction in a circuit. If current is allowed to split, eventually it has to reform. It has to come back together. That's the way circuits always work. It's the geometry of all circuits. So you're always going to have, a redundant equation because there are two junctions where all the same 3 currents or 4 currents or 5 currents, however many you're talking about, are involved. So that's that. The other thing that I'll add here, just let me clear something up here just a little bit as well as far as the junction rule goes, to make things easier on yourself. okay, is, and again, I'm keeping an eye on the comments. So if you got comments, please, you know, put them together here. So let's say I'm going to give myself a little bit of space here. Okay, here we go. Let's say that I have this situation where I have yet another resistor placed out here. Let's say this is R4. Now, I could label I3 right here if I wanted, but notice that I3 is then going to subsequently split here, part of it going through resistor 3 and part of it going through resistor 4. Since there's no resistor in this spot, it's actually not particularly useful to know what this current is right here. Don't even need to know it. What I'll do is I'll say, well, I'm going to label my currents, sure, but I'm going to label the currents that go through resistors specifically. So I'm going to label the current that goes through resistor here, I3, and this one that goes through this resistor here, I'll label it out here, because otherwise it gets a little crowded inside there. I'm going to call that one I4. Do I really care what this current is here or this current is here? It's not ever going to be involved by itself in any loop rule. Because if I go around this loop here that involves R4 or R3, there's never a drop in voltage across any resistance here because there's no resistor in this spot. So I don't really need to have this intermediate current here which then subsequently splits. The other way to think about it is whenever I have a wire here that doesn't have any resistance involved in it, I can just shrink that wire to nothing if I like. So really what this circuit might look like, another way to sort of write it is, there's R1, is something like this. Where they all join instead, they join at one point here. So instead of splitting in two pieces and then splitting into that second one splitting into a third and a fourth, instead I'm just saying, well, it splits three ways. Completely equivalent. It's exactly 100% equivalent to this one. It's just imagine taking that, this spot and this spot and pinching them together. And that's what that does. It eliminates that wire there, which any wire that doesn't have a resistance in it or a voltage applied to it, if it just looks like a wire, you can just pinch it. It's like you can eliminate it and just stretch that join, this join, to be at the same spot as that join right there. That's geometrically how you can think of these, if that simplifies the circuit for you a little bit. You never have to worry about what the current is in this particular branch if you're doing analysis in Kirchoff's rules. Okay, so that was another little sideline. All right, any questions? I don't want to waste your time, talking about stuff that's already clear to you or something like that, or you don't think it's going to be useful. I want to make sure that this is all as useful as we can make it. Anything you want to see specifically that I can go over and help you with? How about the RC circuit? How did folks do with that one? That one's kind of a... Let me talk a little bit, because that's later in the week. You might not have seen this one yet. Let's talk about the RC circuit. The idea of charging up a capacitor. So in an RC circuit, we have something like this. Let's say that I have a battery, and it has some voltage across it, which I'm going to call V. So this is a voltage V across this battery. It could be any voltage I want. And let's say that I have a switch. So this is the symbol that we can use for a switch. It just looks like a wire, and then I can imagine taking this down and touching it here. So these are what we would call the poles of the switch. And then what I have is I have a I don't know. It doesn't matter which order we do this in. So I guess I'm going to put a capacitor here first. So this is mixing some of the stuff that we have. And then I have, in addition to that, I have a resistor, R. And then I close it. So this is a capacitance C, and this is a resistance R. And I've attached it to a voltage V. And I imagine, okay, there's the voltage now is not connected to the rest of the circuit here because I haven't closed this. So at time 0, I'm going to start my stopwatch and I'm going to say I'm going to close that switch. But before that, I know there was no current flowing and I know the capacitor was uncharged. There's no charge on the capacitor at all. Okay. So the technique that I used to analyze this in the, I think that, let me just check. I want to make sure that I'm not getting ahead of us here, but I don't think I did. I think this is lecture notes that are posted. RC, I remember posting them. I remember working on them last week at least. Okay. Well, let's just I'll just go through it. That I want to make sure that we're not. But I remember doing it at least, so I'm not getting ahead of myself. So the idea is you got no. So the charge. So what I'm going to do also is I'm going to say that small letters correspond to stuff that varies in time. So I would use capital Q as the charge on the capacitor when it's done charging, and little q is the charge as a function of time. So it's the instantaneous charge at a particular moment. Okay? So if I close the switch at time 0, I know that the charge in the capacitor at that particular moment is 0. And I know that there's going to probably be some current that goes through the resistor because charge is going to flow through this to get to the capacitor, and then, of course, negative charge is going to flow through this part right over here to accumulate here. So there's going to be some current flowing through the resistor because of the connection to the voltage source. Okay, so little I then, just to remind us here, little I then will be the current. Capital I would be a steady current, but little I is going to be the current, which is a function of time. It might change with time. Okay? And this is how we're going to analyze it then. All right. So how we're going to analyze it, once this is closed, at time 0, I know, so at t equals 0, I know that Q is equal to 0. The charge on the capacitor is 0 at that moment. No charge yet has had a chance to move to the capacitor. Okay. So, by the way, I mean, I in the past I've had a little bit of, this week I've had a little bit of internet hiccup, so if you could all give me like a thumbs up or something like that, that you're still seeing this, that would be great. Okay? Because we had a little bit of a hiccup earlier in the week where I lost connectivity. So hopefully y'all are seeing this and we're not getting any issues. So please let me know. It seems like it's going through, but I want to make sure. Okay, all right. So got some folks at least that are watching still. Okay, good. All right, so thanks, Emmy. Okay, so here's the situation then. I've got charge at time 0. So what I'm going to do is I am going to apply Kirchoff's, thanks Cole, I'm going to apply Kirchoff's rule to this loop. And this is going to work for any time. Okay? So, thanks all. All right, appreciate it. All right, I'm glad it's still going. Okay, appreciate it. All right, so I'm going to use Kirchoff's loop rule and going around here. Okay, so this is what we're going to do. We're going to say across, if I go from here up through the battery, I gain V volts. Okay? Now, as I cross the switch, once it's closed, it acts like a wire. Don't have to worry about it. Okay, so it acts like a wire, no voltage rise or drop across the switch. Now I go from here to here. Now notice, this side of the capacitor right here is the one that's going to get all the positive charge, and this side is going to be the one that gets all the negative charge. So when I cross this, there's a voltage drop across the capacitor. I'm going to use a small v to indicate that, because that voltage drop across the capacitor is going to depend on however much charge there is on the capacitor. When there's none, that's 0. But when it's fully charged, it's as big as it ever gets. Okay? So I'm going to call that V sub C. It's the voltage drop as I go across the capacitor. And the minus sign there indicates that it's negative. Okay, so now I expect that there was current flowing through. Once this switch is closed, there will be current flowing through this branch to deposit itself on this capacitor. Another way to think about that is that current continues going through the resistor here. So there will be a voltage drop across the resistor, which is equal to whatever the instantaneous current is times the resistance of the resistor. And then I'm back to where I started. Oops. That's 0. Now, what's the voltage drop across a capacitor? We know Q is equal to C times V, where C is the capacitance, V is the instantaneous voltage across the capacitor. So what this means, that's using the definition of capacitance. This tells us then that the instantaneous voltage across the capacitor is equal to whatever charge there is across the capacitor divided by whatever the capacitance is. So this is the voltage drop across the capacitor. So I can plug that in here if I like. So the voltage of the battery minus the charge on the battery divided by the capacitance, or sorry, the charge on the capacitor divided by the charge of the amount of capacitance, I times R. Okay, so far so good. So we got two things here that are varying: the charge on the capacitor and the current. But the current and the charge on the capacitor, they're related, because the charge that is flowing onto the capacitor is coming around because of the current. So the rate at which the current so these are related. I is equal to, I have to remember to get my sign right here. It's dq dt. So if there is current flowing onto the capacitor here, that's telling you the rate at which charge is building up onto the capacitor. If I got current flowing towards it through the resistor, it's the rate at which it goes, through the resistor is the rate at which charge builds up on the capacitor. Okay, all right, so here we go. So now what I have is this equation here turns into, with this substitution, it turns into a differential equation. And it's a matter then of solving this differential equation. I'm going to solve, if I solve for Q, which is a function of time now, if I solve for this Q, I will solve for what the instantaneous charge in the capacitor is. All right, and it's just a matter of solving that differential equation, which isn't simple, but isn't terrible either. We talk a little bit about substitutions and stuff like that, and then once the substitution pops out, that it ends up being, it's not too terrible. So I think they go through it in the book. I don't think it's any great, hopefully it's not any great mystery, but that tells you where the differential equation comes from. So I guess I will, oops, I don't want to erase any of my things here, so. Something like that. Okay, so this equation becomes something like dq dt equals, it looks like, what will that be? I bring that over to the other side, divide by r, it'd be v minus q over RC. And then I just do a little substitution here where I do something like, let's see if I can do it, something like Z is equal to V over R minus Q over C. I just define that to be true. And then I see that dz, dt, that's true, that would be 0, and then this would be equal to negative 1 over RC, dq dt. So then I can substitute this in. I can say, well, dq dt is equal to negative RC times dz dt, and I can change this into a differential equation in Z. Just so you know. So then once I do that, then I get something like, well, negative, so dq dt is equal to negative RC times dz dt. So that little substitution there, and that's equal to, and then the right hand side here is the quantity Z. And then I can sort of rearrange this. I can see, well, dz over Z is equal to negative 1 over RC times dt. And I can see that that means this, if I integrate both sides of this, the left-hand side becomes natural log of Z, and the right-hand side becomes negative T over RC plus a constant, which I'll call capital K. Okay, and then what that means is if I can exponentiate this, then I get Z is equal to e to minus T over RC plus a constant. And that's where you get that little exponential coming from that we talked about. And then plugging in the fact that at time equals 0, the charge needs to be 0 in this equation. That actually helps you, that determines what the constant K needs to be. So even though when you do this indefinite integral and you find an arbitrary constant in it, that constant actually is determined from the physics of the situation, that at time equals 0, that's when I started charging it. And you can determine what that is, and it ends up being that the charge as a function of time is equal to, let's see, how does that look? I think it's capital C times V times 1 minus E, and here's that exponential from what we got, from when I do this. So I take the e to both sides, becomes Z is equal to e to the minus, T over RC, and then plus K in there too, so I'll just put plus capital K. That's in the exponent, but that ends up changing into something like that. Okay, so there's that. So that was sort of the end of what we talked about. That was the finish. And we also talked a little bit about circuits and things like that at the end as well, household safety. So anyway, I hope that sort of gave you an idea of some of the mathematics that's associated with doing that, solving the RC circuit. So this tells you what the current is, and if you were to take the derivative of this, that would tell you what the by taking the derivative of dq dt, that tells you how the current changes. So notice that what happens here, just to give you a sense of what the overall result here would look like. The charge on the capacitor starts out 0 and asymptotically approaches C times V with time. Okay, so this is the charge on the capacitor as a function of time. It asymptotically approaches CV as t gets it starts out at 0, because when t is equal to 0, it's e to the negative 0, which is 1. 1 minus 1 is 0, so you get no charge to start. And then at time is equal to infinity, that's when it gets to C times V. How steep this is depends on how t compares in size to RC. So RC is actually what we call the time constant, the capacitive time constant. It basically tells you if R times C is a little number, then this would be a really steep exponential rise to that maximal value. The current looks different. The current starts out at a value equal to V over R. If you were to do the analysis here, you'd find that the current going through the battery would look like it would exponentially approach 0 starting at V over R. So it starts at V over R, its maximum value, and then asymptotically decays, exponentially decays towards 0 as a function of time. So this is the current as a function of time. Starts out at V over R and then asymptotically approaches 0. The reason for that is the capacitor originally has no charge on it, and it's just V is equal to IR, right? It's just, because remember what our original one was? It's V minus Q over C minus I times R equals 0. At time equals 0, when Q is equal to 0, V is equal to IR. I is equal to V over R at time 0 then. When the charge becomes C times V at t is equal to infinity, so when Q becomes C times V, this becomes V minus V is 0, which implies that I is equal to 0. So the current asymptotically approaches 0. So that's sort of how the capacitor works. And RC is the time constant. It tells you about the timing for this. If RC is a really little number, then even for small values of t, this decays really quickly, and this increases exponentially really quickly. If R times C is a really big number, then it really slowly approaches C times V. It slowly goes down to 0. Okay, so I'm going to pause here and ask if folks have any questions, because I know we're over an hour right now, and I don't want to overstay my welcome on this. So I'm gonna pause and see if there are any more questions. Anything, whether it's homework or upcoming stuff or exam format or how's the lab going. I do want to ask too, that is one thing I want to get a little bit of feedback from you, is how is that lab going if you've had a chance to try it so far. Hopefully you have. Sammy seemed to have made an attempt at it to see how it goes. Hopefully it's working out okay. If not, I need feedback so I can fix it. Okay, thanks, Samantha. While I wait for questions to pop up in the chat, I will also discuss one other thing that is related to mechanics about how the course is working. And that is the following. You probably received, early last week, or early this week, or last week, I'm not sure which now, a message about, okay, thanks, Zach, about possibly changing your grading scheme for your course. Good, I'm glad it was fairly easy. But they were talking about, there was an email from from Student Services and from Academic Affairs that asked whether you might want to change to pass-fail grading. The reason that that Century is offering you that option is because we know that you did not sign up for online courses. You signed up for a face-to-face course, and you may feel like this is not fair. It's like, I didn't want to go. But hopefully you're learning something anyway. It seems like it's going okay from my point of view here. But we do want to give you the option of going to pass-fail if you choose. That choice is going to have to be made in the next couple of weeks. But I would offer this. I think it's probably a poor idea to go to pass-fail and changing it. Not basically, if you go to pass-fail, if you earn a C or better, you'll get a pass. If you get below C, you get a fail. The only advantage, really, from your point of view for pass-fail is that pass-fail does not affect your GPA. Doesn't affect your GPA. So if you're really worried about your GPA, but you don't need the course for anything else specific, then going to pass-fail is probably okay. That said, I think for most folks in here, this course is one that where you need it. You need the course. You need a grade in the course. To meet prerequisites and stuff like that at institutions other than Minnesota State institutions, they're going to want to know how you did, and a pass is probably not enough information for them to decide whether you know this stuff well enough for it to meet a prerequisite. The Minnesota State schools, like Metro State and stuff like that, are saying that they will accept pass as meeting prerequisites. So like St. Cloud State and Metro and those sorts of places, yes. The University of Minnesota, though, has not yet guaranteed that they will accept a pass instead, and that, of course, would be a big problem for engineering students. So I would suggest that unless you have a really good reason why your GPA really needs the help or needs not to take a hit here because you think you're going to get something lower than a C or something like that, then I wouldn't change. If you do think that you want to change to pass-fail grading for the end of the semester, ask me first, and then we'll talk about what the ramifications could be for you so that we make the best decision for you. So please send me email on that if you're contemplating it. Please don't just do it, because it could potentially be hard to go back if it's not the greatest choice for you. So, and I also want to make sure that we're making the choice with a counselor or an advisor or something like that involved as well. So please don't just do it. Just consult with me first. So shoot me an email or something like that you're thinking about doing this. But I wouldn't suggest it. I think it's probably best. I think mostly folks are doing relatively well. Things are going okay. And like I said, we've been a little bit more we haven't been quite so strict on things. So I think folks are going to do relatively well in here. And I think folks are going to come out of it with a decent amount of knowledge, enough that I am satisfied that you will have earned the grades that I'm going to give you. So I wouldn't go to pass-fail. I don't think it's necessarily a really good option for you, but it's up to you in some sense, but please ask me before you go and do it. So if there are no further questions, then I'm going to end it here. We're a little bit over. We're at an hour and 13 minutes or something like that now. But I'll pause once more. For questions, I'll wait for about another 30 seconds here, and then I'll sign off. But I want to make sure everyone has had a chance to have all their questions answered. If not, you could just say "see you later, Dr. K" or or whatever. But and responding to Sammy's comment about it, yes, it was fairly easy. I'm glad that the lab was sort of an introduction. Next week's lab, we are going to go into multiple resistor circuits, series, parallel, and that sort of stuff, and then the lab after that will be Kirchoff's rules. So we do have another couple labs using that, Tinkercad. So, okay, well, I'm going to sign off then. Looks like folks are saying goodbye in the chat, so I'm going to do the same. I hope you guys have a great rest of the week. Go ahead and get your studying in. Get yourself ready. I'll have the lecture notes up on Monday, and then we'll have the review then on Tuesday. And we'll open up the exam then on Wednesday. That is the plan for what we'll be looking at next week, and then we'll start talking about magnetism in the second half of the week. So thanks a bunch again. Stay safe out there. Glad to see you, and we'll see you next week. Bye for now. You're welcome.